Hey there. Today we're going to take a look at some exercises that involve searching and sorting, two very, very common operations that you might need anytime that you're working with big chunks of data. For example, in this exercise, we're going to make an array of 1,000 random numbers, probably more than a person is going to be able to feasibly look through. And we're going to use a linear search to go through and see if we can figure out if a number that's there is one that we're looking for, or output that it's not there. So, for anything that involves random numbers, you really should make sure that you set up your random number generator properly using srand of time of null. And this is important so that every time we run our program, it's going to have different numbers every time instead of the same ones. Now, my random number generator is ready to go. I need to make 1,000 random numbers and put them in an array. So first, let's make my array. So my array is going to have 1,000 random numbers in it. And I'm going to need to populate it. So I is 0, I is less than 1,000. And I'm going to go through each element of this array and put in a random number there. So my array of I is going to be a random number. Let's say that we pick a random number from 1 to, say 1 to 10,000. Lots of different options here. Yeah, I think that's fine. Now, we have we have an array of random numbers, and what we want to do is do a linear search to see if a number we're looking for is there. So let's get a number from the user, and then we can ask for it. So cout, please enter a number to search for. You know what, let's make this a random numbers from 1 to 1,000. So I make it 10,000, there's a very good chance the number I'm looking for is not there. Okay, I'll have a guess, and the input will go into my guess. And now I'm going to do my linear search. So all this up to this point is just setting up my array to have 1,000 random numbers, and now I'm going to take a guess from the user and try to see if I can find it. So linear search, actually very simple. For each element in your array, less than 1,000. Now, before I do my linear search, let's talk a bit about this number 1,000 here. Depending on the kind of array that you're working with, sometimes you can get away without using a constant number here, and instead trying to use something, for instance, size of, to tell us what the size of the array is. So, for example, I could use size of my array divided by the size of int, because I know it's an integer array. And this will work perfectly fine. The only reason this works perfectly fine, however, is because I know that my array is always going to take 1,000 numbers in it. So, if you, later on in this course, we'll see how to make arrays that don't actually work this way. So this is only kind of a temporary solution. Sometimes you may need to have some kind of variable that's going to track how big your array is. In any case, our for loop here just goes through each element of the array and checks to see if that's what we're looking for. So if the element that we're looking at is the guess, then we have found it. And we can say, and I think our exercise asked us to find and return the index. So let's say make a I guess it didn't say make a function. We'll just output the index. I think that's okay. So output your guess is found at index, and we'll put the index here. Now, we do want to output something if we didn't find it. So what we're going to do to check to see if we actually found something is use a Boolean variable that says found is false. And we'll assume by default we didn't find it. If we do find it, though, then we'll put it here. Found equals true. Also, since we don't want to output it every time we find that number, in case our array contains duplicate values, we're actually going to modify our condition here and say if the array is what we're looking for and we have not found what we're looking for yet. So if we find it, we'll output your guesses at this index. And if we don't find it, then we'll put could not find the guess. Okay, so let's run this a few times because it's going to be random numbers, so we don't know for sure what numbers are going to be there, and maybe we'll see some different outputs. So let's look for 5. Looks like the first time I ran it, I got lucky. It was actually at index number 282. Well, let's try it again. Oh, looks like it wasn't in that array. Let's give it another try. 180. And all this is doing is looking to see, does 5 show up? And if so, where's the first place it shows up? And it is going to output that answer. Now this goes really, really quick. And the reason this goes really, really quick is because we're only working with 1,000 numbers. I say only 1,000. From a computer's perspective, 1,000 is a pretty low number. If I was working with 1,000,000 numbers, things might get a little trickier. But we're keeping things simple over here. And that's our first exercise. So now let's move on to the next one. So our next exercise is binary search, where we need to create a sorted array of 1,000 numbers. And we'll use binary search to find and return the index of the number that I'm looking for, or print that the number isn't there. You can use the Linux time command to compare the two search algorithms. There's a few other ways to do this as well. I recommend you try it out because the answer that you're going to get is actually going to depend on the computer that you're using. And unfortunately, I don't actually have access to my Linux machine right now. But you can use the time command on the execution of a program to see how long it takes. For now, I think we're just going to try to run our binary search. And here's how we're going to get it to go. Now, first off, our array needs to be sorted, so we can't just make 1,000 random numbers. What I think we're going to do is we're going to make 1,000 numbers, and each one is just going to be I times 10. So this is going to give us an array that contains 0, 10, 20, 30, all the way up to 10,000, just for fun. Okay, now we'll ask for a number to search for. That way we can see if it's there or not. Now here, instead of having a linear array, we can actually have a linear search. We can actually have a binary search. And so the way that we do this is a little bit different. Right now, what we're doing is using a for loop that goes through every element. But in a binary search, you don't need to look at every element. You only need to go see if the element that you're looking for is in 1/2 of your list or not. And what I mean is that if, for example, you're looking through an array for a number and your array is sorted, and you know that the number that you're looking for is bigger than the number you're looking at, you don't have to look at all the smaller numbers. You know it's not there. This is bigger. So you just have to look at the half that matters. So in order to do this, we're going to need a few more variables. So the way we're going to do this is we're going to have one variable that's going to be the minimum, and it's going to start at 0. This is the lowest index where our answer could possibly be. We're also going to have max, which is going to be 1,000 because we have 1,000 numbers to work with. Actually, this should be 999 because that's the last index we could possibly have. And instead of a for loop, we're going to have a while loop. And our while loop is going to go for, there's basically 2 ways that we can end things. Either we find it, or we, or max is going to be greater than min. So the reason I have these 2 conditions is, first off, if I found the number, I don't need to search anymore. I'm done. If I haven't found the number, but I'm at the point where my the boundaries of where the number could appear have crossed, that means the number just can't be in the array. So these are 2 conditions that have to always be true, and if at any point they're not, then I should probably stop. So let's change this here. We're not looking at, I guess we are looking at my array I, but we're going to need to define what that is. So the way that we're going to do that is actually, we'll change the variable name. We're going to make a variable called mid, which is going to be min plus max divided by 2. We'll need parentheses to do this in order of operations. And what I'm doing here is I'm figuring out where's the middle of my array. Once I have the middle of my array, then I know, okay, here's the first place I want to check. Right in the middle, is it bigger or lower than what I'm looking for? If it's bigger, then I need to go on the other side. If it's lower, if it's bigger, I need to go on one side. If it's lower, I need to go on the other. And if it's actually the number I'm looking for, I'm just done. So if my array of mid is the guess, and I haven't found it, then I can just say I found it. However, if my array mid is less than the guess, This means that the number that I'm looking at in my array is smaller than the number I actually want to find, which means that the number I'm looking for must be in the larger part of my list. So that means I need to take my minimum and make it into mid plus 1. The reason I make it mid plus 1 is because I already know for sure that the element at mid is not the right one. I need to go one step further, and then that's my new boundary of numbers I can look at. If my array mid is greater than the guess, this means that the number I'm looking at is too big, and my guess is actually in the smaller side of things, so instead, my max is going to become mid minus 1. So now I've cut off another part. I've cut away half of the list because I know half of it is not going to have my answer. Now, in this case, we can actually do a bit more of a deterministic look at things because we know for sure that my array contains specific values. It contains 0, 10, 20, 30, and so on up to 10,000, or I guess 9,990. So we know for sure that numbers are going to be in this. And what we can actually do just to see how many times do we need to check a number, we can actually keep a count of that. So what we'll do is we'll have int check count. It's going to be 0. And every time I need to check to see if the number is here, we'll increase our check count by 1. Check count plus plus. And at the end of this, we can say we needed check count checks to find our number. Now, if we did a linear search, how many checks do we need to find our number? Well, we need basically however many elements we need to look at till we get to our answer. So let's say, for example, in our previous thing, we did we looked for number 5, and our guess was found at index 180. That means we had to look at 180 numbers to find where we're actually looking. But let's suppose I want to find the number 180 in this list. How many checks is it going to take? Let's find out. Am I missing anything? I don't think so. Okay, no, I made an error. Oh, I have I in here still. This should be mid. There we go. Okay, so I want to look for 180. My guess was found at index 18, which makes sense because each index stores that number times 10, so 18 times 10 is 180. And I only needed 8 checks to find it because the first number that was checked, and actually maybe let's output it. Maybe let's actually show what numbers we're checking. So just so we can see what's going on. The number we are checking now is index mid. And we can actually see what this looks like. So let's do 18 again. So we start in the middle of our list of 1,000 at index 499. This is the 500th element. We know that the number we're looking for is smaller than that, so we don't care about anything index 500 or bigger. We just go straight to the smaller side. Now on our smaller side, between indices 0 and 500, what's the middle? It's 250. So that's the next thing we look at, is 250. Is this... Oh, hold up. Why did this not work? We made a mistake here. So it could not find 18. Well, that doesn't sound right at all. Oh, sorry. We're supposed to be looking for 180. Let me fix this. We're going to look for 180. Okay. Yeah, there we go. So, 500, too big. At index 250, things are too big, so we still need to go in the lower half. At index 124, that's the 125th number, the value stored here is 1,250, because remember, we multiplied every index by 10 to put an element in our array. Okay, well, that's still too big. A 1,250, that's bigger than, or 1,240 is bigger than 180, so we got to go smaller. Okay, halfway from that is index 61, number 610, too big. Half from that is index 30, so it's number 300, still too big. And now finally, the next one we hit is index 14, that's 140, but that's too small. So now we need to go the other way, and our boundaries have been set now. We have index 14 is on the lower side, and index 30 is on the upper side, and we know the answer we're looking for is between there somewhere. Halfway between 14 and 30 is 22. So we look at 22 next. That's too big. So now our boundaries shift from 14 to 30 instead to 14 to 22. Okay, what's halfway between 14 and 22? Well, it's actually exactly 18. And so suddenly we find our answer right there. Only 8 checks were needed, which is better than linear search. With linear search, we would need to do 18 checks, 0, 1, 2, 3, 4, all the way up to 18. But because we know the list is sorted, we can use this algorithm, this process of looking for a number in a sorted list, to expedite how quickly things are going. So if you were to count how many checks are needed to actually get to our answer, it's less than half. Using the time command with this example probably won't give you anything interesting. I think it might actually give you 0 seconds. So my recommendation, if you're trying this at home, is when you're creating your array, don't use 1,000. Use 10,000, 100,000, and maybe 1,000,000, although that one you gotta be careful because your computer might not handle it. With those, you'll see a measurable difference in the time command in terms of how many seconds it takes to run your program. But with just 1,000 numbers, everything goes almost instantaneous. So instead, the way that we can look at how quickly it is just by determining how many times do I need to run this loop. And with binary search, only 8. With linear search, far, far more. So that's why we teach this algorithm. And we're going to start looking at more complicated algorithms very soon. So stay tuned. Okay, speaking of which, bubble sort. Implement bubble sort for an array of 10 random numbers and enter the code into Python Tutor so we can follow the execution step by step. Well, let's write the code first, and then we can put it in Python Tutor after. So first I'm going to take all of this stuff and put it in a function so that we have it, but I don't need it anymore. Exercise 2. We're just going to grab all of this except for the srand. We're going to need to keep that. And this can all go in my other function. Okay, now I need an array of 10 random numbers. We know how to do that. We can actually just steal the code over here. We only need 10 random numbers instead of 1,000. And our random numbers are going to be random numbers. Do we give a range? Nope, let's just random numbers from 1 to 10, I think is fine then. All right, we got 10 random numbers from 1 to 10. Let's print them out just so we can see them. My array I. Just so we can see what this might look like. So here's 10 random numbers, 17709385990. Let's actually space them out instead of using a new line. We'll space them out and then put a new line after. Okay, so there's an array of 10 random numbers, for example. Now, suppose you have this very simple problem. You have an array of 10 random numbers and you need to put them in order. What do? The very basic approach to doing this is what's called a bubble sort. And the reason it's called bubble sort is because you can think of each of these elements as their own little bubble. And in order to sort things, you take 2 bubbles and you look at them and you say, are they in order? And if not, you switch them. You just take one little bubble and rotate it over to the other. And this sort of, cycling adjacent elements process is the whole idea behind bubble sort. Now, there's a few different ways to implement bubble sort. I'm going to do the way that is most intuitive to me, which uses an extra variable. And this is a variable that's called swapped, and it's going to be false. The idea behind the way that I think of doing bubble sort is you will go through all the elements of your list and see if they're in order. And every time you find a pair of them that are not in order, you do a little swap. You basically switch the positions of the 2 of them to put them in the right order compared to each other. If you can go through the whole list and you don't have to swap anything, that means it's all in order, and you're done. There are some other ways to do bubble sort without using this extra variable. Usually it takes more time to do so, but I find this is a fairly intuitive way to make things work. And the idea is that as long as you are swapping things, you're getting closer to the correct answer. It may take you lots and lots of swaps to do so, but eventually you'll reach the point where you have a list that's in order. So while we have, we're going to do a do while. And the reason we're going to do a do while is because I want to do this while we have swapped something. Sorry, while swapped. So the first time, we're definitely going to run this loop at least once, because we need to make sure we go through everything and see, okay, is everything in the right order? At the end of it, if we didn't swap anything, then we should leave. So it's possible we start out with a list that's already in order, and we just say, okay, we're done. But we need to make sure that even though the Boolean starts out as false, later on we will change it if we have to, and then evaluate it at the end. So we're going to start off with an int I equals 0. In here. And for I, in the range from 0 up to the length of the list, which is 10. So we have a loop inside of a loop here, a nested loop. So we're going to keep doing this process over and over until we figure out whether or not everything is sorted. But going through the elements of our list, we don't have to worry too much about that. Now, I'm actually not going to go up to the up to 10. I'm actually going to go up to 9 because I want to compare each element with the one next to it, and I don't want to compare the last element with anything after it because that's outside of my array. So I is going to go from 0 up to 9, not including 9, and if the elements that are there are out of order, then I'll switch them. So if my array I is greater than my array I plus 1, this means that the next element is smaller when it should be bigger, and so I should swap them. And you can do this actually in one line of code, which is my array I plus 1 equals the same thing reversed. So this is just swapping each element. If I have to swap, that means I should indicate that swapped is true. And actually, I should put my my Boolean swapped inside the loop because this is something that I want to initialize every time my loop begins. But while I'm going through all the elements, if at any point I have to swap something, I need to keep track of that because that means my list isn't in order yet. And I'm only going to stop doing this Boolean, this bubble sort once everything is in order. To make sure everything is in order, I'm just going to print it all out. You can steal the code from up above to print it all out. And we'll indicate that this means it's sorted. The sorted array is, and let's give it a run. Oh, we missed, let's see. Oh, I do need to declare this out here because otherwise it does the while loop, the while condition here can't see things that are inside of the do braces. So I need to declare swapped out here, and then inside I can set it to begin as false. I know that because it says swapped was not declared in the scope, and what that means to me is, oh, in this line, number 76, swapped is something that it doesn't recognize if it's defined inside of this loop here, because as soon as you exit the highlighted piece of code right here, any variables that were initialized here, such as I, are no longer visible. We don't know what they are. So I need to declare swap first, and then I can change the value over here. Okay, let's give it another try. I'm looking for input for some reason. Oh, you know what? I may have made missed one important thing, which is I need to make sure I is actually going up. It's an important thing to have in my or actually, wait a second. What am I missing here? I'm missing no, I is going up. Okay, what mistake have I made? Let me think here. I don't need this here. That's not relevant. Run this again. Okay, something weird is happening. I think it's maybe the case that this line of code isn't doing what I want it to do. Maybe let's get an idea of what's actually happening here. We're gonna copy this into here. Whoop, I can't edit it while it's running. Let's stop. This is a good way to troubleshoot. I made a mistake. Let's see if we can figure it out. So here we're gonna have the unsorted array is, and we're gonna print everything out, and then we'll see what's happening. Okay, so apparently it's not actually moving things around in my array. So probably this line of code here isn't doing what I want it to do. So let's change it. My array I sorry, let's make a temporary variable that we can store my array I. Then my array I can be replaced with I plus 1. And then my array I plus 1 equals my array I. I wouldn't be surprised if this line of code works in Python but not in C++, but let's do a little check to see if that's actually what happened. Of course it is. Oh, but that's not ideal. We suddenly deleted a bunch of numbers and replaced them with ones. So that's probably not correct. I mean, we got it sorted, but all the numbers seem to have changed into stuff they're not supposed to change into. So what I think is happening here is, let's see. In my first iteration, so I think I know what's happening here. And what I think is happening is, actually, So the first time I have my numbers, the 8 and 9 should be swapped. The 9 and 2 should be swapped. But then the 9 actually didn't get put where it was supposed to be. And that's because I made a mistake right here. My array I plus 1 should be the temporary variable. So if you were able to see that before I did, then good on you. So we put the temporary value from my array into here. We replace my array I with the next number, and we put the next number is our temporary one, so that should swap things. So let's give this one more shot. There we go. Okay. Let's actually space this out a little bit so we can see everything nice and clearly. Okay, and let's see what happens as we do our bubble sort. So here's a random array of numbers, 7706097447. Now, the first time we do bubble sort, we go through and we look every time to see, okay, are these actually in the right order? So 7 and 7 are the same number, so there's not really much to do there. However, 7 and 0 are out of order, so we're going to swap these, which means that we're going to have 0 here, and 7 is going to go next. And then 7 and 6 are out of order as well, so the 6 is going to go here, and the 7 is going to go next. 7 and 0 also out of order, so 0 is going to go here, and 7 will go here. Now, 9 is bigger than 7, so we're going to leave this 7 where it is and move on. Now, this 9 is bigger than this 7, so they're out of order. That means I need to take this 7 and put it right here. So it ends up there. 9 is bigger than 4 as well, so this 4 right here is going to be put here, and the 9 is going to move here. 9 is still bigger than the next 4, so this 4 here gets shuffled over into here, and we have 9 here. And then 9 is bigger than 7, so we swap 7 and 9. Now, this may be tricky to follow, and I don't blame you if you had some struggles following it. So let's actually try and do this in Python Tutor so we can see what's happening. And while we do so, we're actually going to get rid of... Once we do so, we're actually going to get rid of the printing, because Python Tutor is going to actually show us what's happening. So let's go to Python Tutor, to C++. We're going to get rid of the exercise from before, because we don't really need that. We're going to get rid of the printing of all the numbers because we don't need that either. So we're not going to print anything. I'm not going to print anything. We're just going to look at the actual algorithm. Let's give it a go. Oh, and we don't need to print that either. Okay. Whew. Okay, 313 steps to go. So this was not a fast algorithm, but let's see what happens. So we're going to fill up our array with random numbers. And so you can see on the right here, maybe let me zoom in a bit so you can see a little better. It's a shame that I can't have this visible at the same time as the button. Maybe if I do this, there we go. Okay, so here's my random list of numbers. All right, now this is clearly out of order, so we're going to need to sort things. So let's see what happens as I go through. So first off, my 4 and 6 are in order, so everything is fine. 6 and 7 in order, everything is fine. But 7 and 2 are out of order, so now they're swapped. Let's swap. So 7 and 2 are out of order. 7 and 4 are out of order, so we gotta swap them as well. 7 and 4. 7 and 7 are fine, so we leave them. 7 and 1 are out of order, so we swap them. 7 and 8 are in order. 8 and 0 are out of order, so we're gonna swap those. And 8 and 2 are out of order, so we're gonna swap those too. And now, that's the first time we've gone through and tried to push everything in the right direction. And I recommend you actually take the time on your own to kind of explore how this looks, and you can see, I'll kind of zoom through. We're just basically pushing everything around, swapping elements until eventually at the very end of this, we end up with a sorted list. 0, 1, 2, 2, 4, 4, 6, 7, 7, 8, and everything is in order as it should be. So that's our bubble sort. Not the best way to sort things, but it is a way to sort things, and it's worth at least understanding exactly how it works. I highly recommend following the steps in Python Tutor so you can actually see what is happening to your array as you manipulate it. So that's our first sorting algorithm, and we'll finish off with one more after this. Our last sorting algorithm is going to be what's called selection sort. So we're going to do the exact same thing. And you can use the time command to compare the two times if you're operating on Linux. You can also use what we did in our first exercise and put in a number to check how many steps it takes. But mostly I'm going to focus right now on just getting the selection sort process working. And so the idea behind selection sort is essentially what's shown in this diagram here, which is we're going to go through our array to find the smallest element, and we're going to put it at the beginning of our array. And we're going to keep doing this over and over, basically finding the next smallest item every time until we put all the smallest items at the beginning of our array, and our last item left is the biggest one. And then everything is in order. So let's try to make this work. Now, let's make another function to put away our code from before. We can leave some of this here. We're not going to use swapped anymore. We have a very different approach that we're going to take. So let's cut all this out. We're still going to keep a random number generator in here, but I'm going to cut everything first. I'm going to grab back this part. So starting off, we're going to make 10 random numbers and print them out so we can see what they are. Okay, we got 10 random numbers. We want to put them into order using the selection sort algorithm. So there's a few things we're going to need. First off, we're going to need to know what is the first sorted index, which initially is going to be 0. So the idea here is that there's going to be some chunk of our array that's going to be in order, and we want to know what is the actual spot where that stops. I guess it's not the first sorted index, it's actually the last sorted index. And everything that's at this index or before is going to be in order. Now, our list is, we are going to go until the last sorted index, as long as it's less than 10. Basically, once we have put all of the elements up till the 10th one in order, we're done. Now, until we reach that point, what we want to do is try to figure out what is the smallest element in our list. So, int min element is 0. We know that our random numbers are all going to be between 0 and 10. So, so let's actually have our minimum element be -1. That way we know for sure that, that it's the smallest. And actually, I'll put this inside my loop. So, smallest element is -1, which means I'm always going to be finding something that's... oh, sorry, not -1. It's going to be... I have this backwards. We're going to say the smallest element is going to be 11, because we know for sure everything in our list is smaller than 11. There are other ways that you can work around doing this. In fact, probably let's actually go with the better approach, which is our minimum element is going to start off as my array at the last sorted index. So for now, we assume this is the smallest element. Now, we need to go and figure out, is there a smaller one? So, for I equals last sorted index, oops, not with brackets, +1, I is less than 10, I plus plus. We're going to go through and try to find the smallest thing that's there. In addition to having the min element, we actually need the min index as well, which at first is going to be our last sorted index. But as we find an element that's smaller than that one, we need to keep track of where it is. And so we're going to use this variable for that. Okay. Now, if my array I is smaller than the minimum element, this means I have a new minimum element. So my new minimum element is going to be that number, and my minimum index is going to be I. So this means I found a new candidate for the smallest thing in my list that I have to work with. Okay, now, once I have gone through the whole list, I found the actual smallest element. And so what I'm going to do is I'm going to need to swap that with whatever is at the last sorted index. So I'm going to need a temporary variable, which is going to be my array at the last sorted index. And we're going to replace that with the min element. And we're going to go to where that element was, which is at the minimum index, and put in our temporary number there. Now, is there anything that I'm missing? I suppose we'll output to make sure that it works. Sorted array is... And then finally, we also need to increment our last sorted index, because now we know that everything up till there is all done, so we go one step further. Okay, let's see what happens with this. I hope that it works. I guess we're going to find out. Oh, I have an error. Let's find out. I'm missing a brace somewhere. Line 93. Oh, I have an extra brace over here. I don't need that. Yeah, that looks sorted to me. So let's see how this actually worked in practice. We're going to put this back into Python Tutor and go step by step to see what happened. Okay, Python Tutor, let's show us what's going on here. We're going to put in our code. We're not going to print anything out because we don't need to. Oh, I need all of my code. I'm going to grab everything, and we're just going to delete the exercises we don't need. The printing commands, because we don't need to print anything, and so all we're going to have is just the algorithm itself. Okay, let's visualize this execution. Okay, I got my 10 numbers here. We're going to put some random numbers in there. And oh, we can already tell this looked a little bit faster. 216 steps instead of 300 for bubble sort. So let's see how this works. here's our random numbers. A bunch of those over up here. Okay, so let's try sorting this out. So we're going to start off by assuming the smallest number is 8, which it's definitely not. And we're going to go through our array to find what's really the smallest number. And then once we find it, we're going to swap this 8 with that number. Just from a glance, we can already see that 1 is the smallest. So the first time we go through our list, we look at everything. We're going to keep track of what the smallest thing is. And then we're going to put this 1 over here. And we're going to put this 8 over here. So we go through, we look at all the numbers. And at the very end, once we hit I, we figure out that this is the smallest, and so we swap it into place. So 1 goes there, and 8 goes at the end. Okay, so now 1 is in order, and now we need to look at the rest of the array to figure out what to do there. Well, it turns out 4 is actually already in order, so nothing's going to happen for this step. We're going to go through everything, nothing's going to change. 4 is the smallest number already. Okay, 8 is definitely not the smallest. 4 is going to be the next smallest number if we're looking at this part of our array. So we're going to swap this 8 with this 4. Going through. We figured out that 4 is the smallest, so we swap 4 and 8. What's next smallest? It's not 7, it's going to be 5, so we're going to end up swapping these two. Can speed along a little bit. 5 and 7. 7 is actually bigger than 6, so we're going to put the 6 where the 7 is and the 7 where the 6 is. So we swap those. We're going to swap this 8 and this 6. That's the next smallest. And we'll swap this 8 and this 7, and then everything else will be in order. And we're done. So that is selection sort in a nutshell. Hopefully this was useful. This is not something I would expect you to be able to create on your own. In a test, for example, but knowing how this algorithm works is something that I would expect you to know because this is the kind of operation that happens all the time in computer science. And knowing about sorting algorithms is something that you're going to see quite a bit in your computer science future. So if you're interested, there's plenty of articles and such out there all about sorting algorithms. My recommendation is definitely try coding them yourself, get some practice with them, see if you can figure out how to make these sorts of things work because they're going to really help you solidify your understanding of how to program. So that's it for this video, and I will see you in class. Goodbye.